Hey, chemistry students, it's week number 2. Like I said, this is all going to be kind of new for both of us. Um, so, this is new content for you. So, please pay attention. If you have questions, get with me on my office hours. Remember, that's Monday, Tuesday, and Wednesday from 9 to 10 o'clock in the morning, or on Monday from 5 to 6 p.m. You can get onto Zoom, ask me questions. If you look down in the comments below, I'll have my link for my Zoom. You will need a password to get on there. I sent that to you on Remind. All right, take it easy, and here we go. Okay, so this should really be a quick review from middle school, but just a reminder, if you want to look into this a little bit more, this is Chapter 10. So there are 3 states of matter that we really worry about in chemistry: solid, liquid, and gas. We're going to deal with liquids coming up later on. We've pretty much been dealing with solids. You don't have to worry about that. The important one here for today, for this week, is we're going to look at gases. Okay? So here you go. Okay, so when we're dealing with a sample of gas, that sample is basically defined by 4 different variables. Our first variable is N. This is how much of the gas is there. So how do we measure how much of something we have in chemistry? Well, that is using the units of what? That's right, moles. So N is our number of moles. Important number. The second variable that we have to worry about with a sample of gas is P. P is the pressure. Because a gas is compressible, we can force it into a smaller volume, and by doing so, we increase our pressure. So the greater the pressure, the more gas we have in our container. Now, pressure is normally measured using one of 2 different units. There's a lot more than this, but in chemistry we pretty much use these 2 units exclusively. The first one is the easiest, and that is atmospheres, ATM. Basically, 1 atmosphere is the pressure of air at sea level. So in most cases, if you don't know what the pressure is exactly, we work with 1 atmosphere. I like atmospheres because, hey, 1 is a really easy number to multiply and divide by. But more specifically, we would use pascals, or actually kilopascals. And 1 atmosphere, the pressure of the atmosphere at sea level, is 101.325 kilopascals, kPa. So the important thing to remember is whatever units you are given in your problem, those are the units you're going to have to use as you're doing the calculations. Keep these straight, and it helps things along. In fact, later on we're going to have a variable that you have to choose which value for that variable based on these. Alright, so I mentioned volume. How much room does that gas take up? And if we increase the pressure, or if we decrease the volume, the pressure changes. So volume, again, an important variable. And we normally measure volume in liters. We might measure it in milliliters, but again, generally liters is what we're going to be using. And the last one, temperature. Think back to your middle school or physical science days. The particles of gas are moving around, and the temperature is basically a measure of how fast they're moving. You increase the temperature, they move around faster. When that happens, your pressure goes up. So temperature is very important with this. And A very, very important thing to keep track of is temperature must always, always, always be in Kelvin. That's abbreviated without a degree sign. You don't say degrees Kelvin, it's just Kelvin, and that's a capital K. And if we have to convert, 0 degrees Celsius is equal to 273 Kelvin. If some of you folks out there are a little pedantic and kind of know about this already, it's actually 273.15, but for our purposes in this class, we're just going to use 273. We're going to make it a little bit easier for us. Now, how are these all related? Well, generally speaking, I would go through this over the course of several days, and I would introduce you to one law after another until you had 5 different gas laws, and then we would put all 5 of those together to form one single law. Since I don't have that time, we're going to start off with that single law, and that is the ideal gas law. Now, why are we going to start with this one? Because if you know your ideal gas law, you can figure out all the other ones. So, the ideal gas law is PV equals N R T. Now, you recognize PV, N, and T. Well, what is R? R is our gas constant. The value for R depends on what the other units in the equation are. What units are you using for pressure? What units are you using for volume, etc.? I'll get you the values for R here in a minute. But let's talk about how these gas laws are related. Like I said, if you know the first one, the ideal gas law, then you can figure out these others. There's really 5 of them, but what I care about is I care about the ones that relate pressure, volume, and temperature. So the other 3 laws are Boyle's law. And if you're in chemistry, I really don't care that you know the name. That's not really that important. However, if you're on the academic team, you need to know that name. Why? Because it will come up in competition. We have Charles's law, and we have Gay-Lussac's law. Now, Boyle's law applies if you have a constant temperature, whereas Charles's law applies if you have a constant pressure, and Gay-Lussac's law applies if you have a constant what? That's right, volume. So, basically, the basic form, like PV equals nRT, for these 3 laws. So it takes the number of moles and whatever the constant is, and R, and it rolls them all together into a single value. So the value of K in Boyle's law varies based on the sample of gas you're working with. So this form of the law doesn't really help us very much. Neither does this form of Charles's law, V equals KT. We will not use these forms of the law. And finally, P equals KT. However, where they do come in very, very handy is if we're working with a single sample of gas and the conditions change. If the pressure, volume, and temperature are changing for that gas, then as long as it's the same sample. R would remain the same value, and N would remain the same value. So that becomes a constant. So I would end up actually canceling it out. So what I would end up with is the form P1 V1 over T1 equals P2 V2 over T2. So based on that, if I have a constant temperature, they'll cancel out, and I can just ignore it. So what does Boyle's law look like? Well, that's it right there. P1 V1 equals P2 V2. What does Charles's law look like? Well, it's a constant pressure, so if I cover up P, I get V over T. V1 over T1 equals V2 over T2. What about Gay-Lussac's? P1 over T1 equals P2 over V2. And these are the forms of the equation you'll be using. Now, I promised you one more thing, and that was a value for R. Well, there's really only two values you need to know for R. And that's based on the units. The first value is 0.0821, and the units are liters times atmospheres divided by moles times Kelvin. So if you're using atmospheres as your pressure, that's the value you need. The other value is 8.314 liters kPa over moles Kelvin. So again, if you're using kPa, this is the value you'll need. So, all right, let's work some problems. Okay, here's our first problem. A sample of oxygen gas has a volume of 150 milliliters and a pressure of 0.947 atmospheres. What will the new volume of the sample be when the pressure is 0.987 atmospheres if the temperature remains constant? So, the form of the equation that we need is Boyle's law, and that is P1 V1 equals P2 V2. So what is pressure 1? That is 0.947 atmospheres. What is V1? That is 150 milliliters. What is pressure 2? 0.987 atmospheres. What is V2? Well, I don't know. That's what I need to find out. I can rearrange this equation ahead of time, or I can simply fill it in like this and then rearrange it. So to get rid of the 0.987 atmospheres on this side, I divide both sides by it. So those cancel out. I'm left with V2 by itself over here. That's 0.947 times 150 milliliters divided by 0.987. My atmospheres cancel out, and when I do the math on this, I come up with 143.9209, yada, yada, yada. And that rounds off to 143.9, and the units I'm left with are milliliters. There's our answer. That's all it is. Plug and chug, guys. So, problem number 2. A sample of neon gas has a volume of 752 milliliters at a temperature of 298 Kelvin. What will the volume be at 323 Kelvin if the pressure remains constant? Well, constant pressure is Charles's law. That's V1 over T1 equals V2 over T2. Again, I can rearrange this ahead of time if I know what I'm looking for. I'm looking for volume, so I could rearrange it so volume 2 was by itself first, and then fill in my numbers, or I can fill in my numbers afterwards. It doesn't really matter. Personally, I like rearranging it. So if I want to get volume 2 by itself, I need to multiply times T2. T2 cancels out on that side. So I'm left with volume 1 times temperature 2 divided by temperature 1 equals volume 2. So volume 1, 752 milliliters. Temperature 2, 323 Kelvin. Temperature 1, 298 Kelvin equals V2. My Kelvin will cancel out. When I do the math, multiplying and dividing, I come out with V2 equals 815.0872, yada, 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 which rounds off to 815 milliliters. If you notice, milliliters are the only units I have left there. I'm dealing with a volume, so I want milliliter. I want liters or milliliters. Okay. Let's try another one. The gas in a container has a pressure of 305 kPa at 25 degrees Celsius. A warning label on the can says to store below 52 degrees Celsius. What would the pressure be at that temperature? Well, the volume is staying the same, so that's Gay-Lussac's law. So I've got P1 over T1 equals P2 over T2. Again, I can fill it in or rearrange. I'm going to go ahead and fill it in first. Pressure 1 is 305.0 kPa. Temperature 1 is 25. Oh, wait a minute. It's degrees Celsius. What do I have to do to convert? I have to add 273 to my Celsius. So 273 plus 25 gives me what? 298 Kelvin. Warning label says to store below 52 degrees Celsius. 273 plus 52. That's going to be how much? That's right, 325 Kelvin. What would the pressure be at that temperature? Well, this is nice. I got pressure on top, so it makes it a little bit easier to work with. What I'm looking for is on top. If I was looking for temperature, I would have to get that on top of the line first, and then I could get everything else on one side and what I'm looking for on isolated on its own side. All right, so at this point, how do I get rid of my 325? Well, I multiply both sides by 325 Kelvin. So when I do that, it cancels out on this side. Pressure 2 equals 325 Kelvin times 305 kPa divided by 298 Kelvin. My Kelvin temperatures cancel out. I do the math. I come up with 332.6342. Yada, yada, yada. That rounds off to 3 significant digits. Why 3 significant digits? Well, 298 Kelvin, that's 3 significant digits. So even though I've got 4 here, I've got 3 there. So that is 333, and what are my units? Well, the only units I have left are right here. Kilopascals, kPa. And there's my answer. All right, last problem. A balloon has a volume of 50 liters at 25 degrees Celsius and 1 atmosphere. How many moles of gas are present? Well, I'm looking for the number of moles. What equation do I need to use? That's right. PV equals nRT. I'm looking for a number of moles. I could rearrange this ahead of time. Or I could fill it in and then rearrange. Again, I like rearranging if I know what I'm looking for. I know I'm looking for N. How do I get rid of RT on this side? Gotta divide. That means I divide on this side. RT cancels out. And I've got PV over RT equals N. So what is my pressure? My pressure is 1 atmosphere. That's good. I like that. 1 atmosphere is easy to work with. What's my volume? My volume is 50 liters. What value should I use for R? Well, looking back on the notes, the value for R should be what? That's right. Since I'm using atmospheres, my value for R should be 0.0821 liters times atmospheres divided by moles times Kelvin. And my final term there is temperature, and that is going to be 25 degrees Celsius, which is how much? That's right, 298 Kelvin. All right, so at this point, I can simply do the math. So I've got atmospheres here, I've got atmospheres there, they're going to cancel out. I've got liters and liters, they're going to cancel out. Since these are on the bottom of a line here, it's going to go up on top. So Kelvin and Kelvin are going to cancel out, and I'm going to be left with moles. So when I do that, I get 2.043669 yada 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 moles. So that gives me what? Let's see. I'm going to round it off to 3 digits. 2.04 moles. And there's our answer. What's the second half say? What volume would it occupy at 10 degrees Celsius and 86.63 kPa? Well, which form of the equation am I going to use for that? P1 V1 over T1 equals P2 V2 over T2. My R value will remain the same on both sides of this equation, and my number of moles will remain the same. It's still going to be 2.04 moles. I could put it in, but if I did, they'd cancel out. So let's not even worry about that. So we go to this form of the equation. So what's my initial pressure? Well, that was 1 atmosphere. It's using kPa in this form for my pressure. So why don't I convert that over to kPa? That's actually easier. I can do that in my head. What is 1 atmosphere in kPa? That's 101.325 kPa. What is my initial volume? That was 50 liters. What was my initial temperature? That was 298 Kelvin. So what is my second pressure? That's 86.63 kPa. What is my second volume? I don't know. That's what I'm looking for, V2. And my new temperature is 10 degrees Celsius. That's 283 Kelvin. I can do that addition in my head. So, I'm going to divide both sides by 86.63 kPa. I'm going to multiply both sides by 283 Kelvin. That way I cancel out on this side. I'm not even going to go ahead and write that out. I'm just going to let you know that I did that. So when I come up with V2, I get a value of 55.53777. So that's going to round off to 55.5. So I've got 3 significant digits in my temperature. And the units, volume, will be in the form of liters, because I have liters right here. My kelvins will cancel out, my kPAs will cancel out, and I'll be left with liters. There you go. So, if you have any questions about how to do these, if you need any help with them, then feel free to get a hold of me during my office hours. If you want, you can even send me an email. That works just fine. So, you have a homework assignment. 0.0821 liters atmospheres divided by moles Kelvin equals 8.314 liters kPa. So we have 5 problems here. This is available for download. I will send you the information on Remind, and if you look down below in the comments, again, I will have in the description, I will have the link to this on OneDrive. All right, guys, have a good week.